he was continuously in touch as he was the chairman of TCC. Right. This is just a enlarged photograph of one of the core samples on left side, that is its size, but then enlarged, where we can see exactly that if any core sample had cultural material, that was clearly seen when it was cut or sliced in two parts. Just another photograph where we can see baked bricks pieces and pottery as well. These are the two common things which are found. In certain areas they are quite thick and as deep as 17 meter. In addition to baked bricks, pottery, there may be small broken pieces of toys, bangles, and many other things. Just another example of enlarged core sample. Here, this thing is mentioned that you can see laminations in this particular core in the subsurface. Now, this sort of lamination, dark patches, dark layers, and then slightly lighter tone, this is typical fluvial river deposit. And normally darker, it contains more organic matter as well as the size of grains, the size of material is smaller, which shows little dynamic activity or velocity of river water, whereas lighter sediments, they are relatively coarse sediments, probably fine sand or medium sand. This is the way we organized our data after photographing each and every meter, and then we combined, integrated all the data in one photographic plate. For example, from 1 to 12, this represents the one borehole, that is 46 number. So in this way, we organized all the data, 55 boreholes. These are just few examples to show here. A recovery of core in each sample was not always 100% due to various factors. As you can see in these 6 and 7 core, the recovery was minimum as the material is composed largely of baked brick pieces and pottery, and this is something normal. When that core is pulled up, normally its material drops down. So for sand, this also happens, and we used metallic pipe and different technology, because in some photograph you can see metallic pipe. As in this case, the last one, it's a metallic pipe because it was sand, and for that special technology was used. And that was another thing I should mention here, that every time we encountered sand, pure sand, that was indication of either channel or channel levee deposits of river, we stopped there because we thought that from there in the subsurface it may be only river deposits. However, at one or two places we continued even in sand, just expecting that it may be possible to encounter cultural material again, but it was not the case. Another photograph. Right. Based on this study, what I said, the detailed study was carried out centimeter scale, and then ultimately the data was plotted on this log, which we call it sedimentological log, which has detailed description and log on left side with the photograph on right side as well, so that it has comprehensive information for anybody who can look at it. Another example of similar data, and this exercise also is carried out for all the drillings 55. As we said that we are interested to know these sediment in the context of the Indus River dynamics, So it is very important, in addition to looking at the features, laminations, layers, to look at the grain size data as well, because this grain size data that can actually further strengthen our findings, interpretations regarding the Indus River course and its flows. So this is just interpretation of data where we can see that this particular sample, which is of 3 sample of core number 1, its size on log scale phi is 7.8, which is fine silt, whereas this curve, a cumulative curve, that shows the behavior of the sediment population, and it can tell us even more about the sediment, that whether they were naturally deposited due to the flow which has strength variable, or it could just be from a dump. If it has a smooth unimodal curve, then it is quite possible that it's a fluvial deposit, river deposit, whereas multimodal, having this balloon shaped more than 1, 2, 3, then it may give indication that this is either dump or may not be deposited from river. In this manner, we collected about 300 samples from 55 cores, which have been analyzed. As you can see in this, that this also a bimodal curve, and reaching at this stage and interpreting data, producing logs, then another stage is to actually have a profile or cross-section of subsurface on any given line. This particular diagram, along the sample location, you can see yellow lines starting from northeast, that is AA, then B, C, D, E, F, G, H. We produced profile to see the nature of change in the subsurface going away from the main excavated area. So this is section AA. I just showed you the location, that is northeast direction. These are various boreholes, 52, 53, 54. All three boreholes, they are rich in cultural material. Uh, quite this particularly 53, where we can see that right from start, from the surface, this cultural material, baked bricks and pottery. The red symbol that shows pottery, whereas the lighter color that shows baked bricks. In core 53, we can see some black spots. These are for the ash, whereas it also contains certain sand lances. So in this manner, we produce about 8 sub cross sections for better understanding or behavior of these cultural as well as natural layers. DD, there are certain cross sections. You see, there's minimum material, cultural material. Most of the deposits, they are of Indus River deposit. This yellow color, that shows sand, whereas gray color, that is silt and clay, and the green color, that is silt and clay with some laminations and layerings. There were spots in certain location, as on the left side, this orange color. That orange color is for a thin layer of pottery, which is about half a meter to 1 meter in thickness. Now, this has to be interpreted that what it means actually to have that thick deposit of pottery at certain places, and similar thing has been found at different locations in borings. Right. Now, this is the area which was second objective of our work, which needs further exploration in terms of interpretation of satellite images and historical images as well. Uh, in more detail, Professor Joe is going to talk about it, but my findings also, they indicate that there has been greater influence of Indus River on Mohenjo-daro, not only Mohenjo-daro but other settlements in the area, as we can see Diji, Takri, Chaundaro, and many more which are not listed here. So understanding the Indus River movements, it's very important, as this satellite also shows that Indus has been shifting its position in the past. Right after 5,000 years ago, there is another element that worldwide there was a climate change, aridification, and even the sea level, which was rising fast before 5,000 years ago, it almost stopped at 5,000 years. So that is another area which has to be taken into account when looking at these things. So this is larger image. If we go in further detail, this is a satellite image of Mohenjo-daro. This is the behavior of Indus when it enters in Sindh. If we can see, there are a lot of meanders and its channel in the uh, waste of the present course. What does it show? And even these lighter tones within this vegetation, these all are deposits. Looking at their reflective index as well as their spectral analysis, that will reveal that in this area, even Jekambad, Tul, Shahdad Kot, there are all these deposits, they are by the river. When did Indus go there? That is a question as well. Was it after the Mohenjo-daro? Did it migrated in that direction? And so that Mohenjo-daro area faced scarcity of water? These are various questions which are to be looked at in the light of these studies, in particular the shifting of Indus River and flowing, because it has been shifting between Rodi Hills and the Kirthar. I don't know how many times, maybe future can tell. Regarding our first objective, that was to know the real extent of Mohenjo-daro. As I said, that this is a preliminary study as well as results. Some final phase is still in progress, so we just stop short of the final conclusion. Once that study is completed, report is submitted, we will definitely produce those results at some other forum. Thank you very much.
Professor Dr. Joseph Schulderin will be talking about his studies.
Good afternoon. Can everybody hear? I want to extend my thanks, deep thanks, to the Ministry of Culture of Sindh, and I owe my introduction to the Indus Valley geoarchaeology through my colleague Dr. Rita Wright, and my apparently nascent involvement in Mohenjo-daro to Dr. Michael Janssen, and I want to especially extend my thanks to Dr. Lashari for advocating for this project. I'm going to provide a little bit of a different perspective on the geoarchaeology of the Indus Valley. It stems, as I had indicated earlier, from research that I had done in the area of Harappa with the Beas River Survey, and it has caused me to take a very sort of overarching view of what the Indus is like and how we can start to look at joint perspectives on site settlement and river mobilization. So if you'll bear with me, we will proceed through that journey. The objectives of the study are really to connect the fluvial systems or the river systems of the Indus with settlement geography, but not just settlement geography in the traditional sense, but archaeologically in terms of preservation geography. There's a huge difference. As my colleague Dr. Solangi had indicated, the Mohenjo-daro site itself was probably much more extensive, and there are probably very many neighboring sites that are simply buried beneath layers and dozens of meters of alluvium. We have to take that into account. Secondly, the centrality of the drainage basin as an investigative parameter is something that has been overlooked. It's a basic point in geomorphology, and I'll talk about it in a minute, and I think you'll see exactly how basic a context this is for understanding why sites are where they are and why they end up where they're not. And that's another major issue that I'd like to address. Finally, I'd like to go through some reconstructions for the upper Indus, and then I'd like to link my work to the upcoming work on Mohenjo-Daro with the work of Michael Janssen and Dr. Solangi, and then we are going to have a concluding series of remarks. You cannot understand anything about how river systems work without very basic fundamental understanding about how water systems and rivers behave. The most simple and the most elegant model that I've ever seen was one that was put forth by Dr. Stanley Shum. Dr. Shum indicated that essentially once the river empties out of a mountain range, in this case the Himalayas, there is a series of tributaries that come together and become increasingly larger drainage trunks. The trunk is the basic river stem. And what happens after that is that they mobilize and they form a single super trunk. And then eventually when they get down into the confluence of the oceans and the basins, you will eventually have a drainage that extends all over the place. Anybody who looks at the Indus sees a classic version of this model. If you look at Zone 1, the upper Indus essentially conforms to the configuration of the Chenab, the Sutlej, the Ravi, the Beas. They all come exiting from the Himalayas and they come down. Then they form one stem south of the Five River Divide, and then once you get down into the basin, into the delta, you have the delta itself. Concomitant with that is the fact that the sediment gets increasingly mobilized as you move down the system, so that your upper drainages are relatively simple. Your central drainage is where everything comes together, and then when you go down into the bottom, lower Indus, it becomes chaotic. And if you need any proof of that, look at the archaeology of Egypt, how chaotic it is at the delta. Look at Mesopotamia, how difficult the settlement systems are to put together at the mouth of the Persian Gulf. And if you want to go into North America as another indication, all you have to look at is the Mississippi River, where you have alignments of primary sites along the primary stem, and when you go down into the delta, it becomes chaotic. Part of the reasons of those are complicated. They are related not just to the action of the river itself, but once you get down into the chaotic zone, if you want to call it that, there is, as Dr. Solangi indicated, the influence of marine transgressions and regressions. So the mixture and the complexity of these systems is enormous. And that's why Mohenjo-Daro, because of its location in such a complicated area, is going to be a very difficult task to unravel. But as Dr. Solangi indicated, all those abandoned river channels are expected. They have to be there. And if you don't know that they have to be there, then you're really not doing things in an appropriate fashion. So that's kind of the basic scenario that I want to look at. And so now I want to get into some of the summary things that we did in the Beas River Survey. The first thing we have to do is to look at the nature of these alluvial landforms, and they're very complicated, and I'm not going to go into all the details, but the connection with them and chronologies. In other words, you have to get dates, and more dates. And those have to be linked to archaeological sites. The archaeology is going to give you dates because you're looking basically at a 5,000-year window, and you're also going to get dates from the organic material in the riverbed. So this is an interesting challenge. The other thing is you have to look at the connection between occupation loci, places where people actually build their mounds, and the rivers themselves and the environments in which they utilize. One of the key issues here is that people build mounds in areas that are naturally well drained. So they would not build their mound in areas that are extensively flooded. So anytime you see a rise in the landscape, a fluvial landscape, then you will probably have some kind of a mound. And the mound tends, according to the law of uniformitarianism, to build up and up and up and up until you get a big mound, a tell in the Middle East, a mound in the Midwest US, and that is the nature of how these sites evolved in a very generic sense. You have to look at these sequences not just on a regional basis or a grand scale, as we talked about earlier, but also by the locality itself, because there are local controls, there are regional controls on all of these systems. And then, of course, there is the crazy variable of culture, which creates something that's not necessarily deterministic by environment, but also has to do with traditions and where people live. And ultimately, one of the more important issues is looking at climate as an element in the entire operation, because as we know, there were catastrophic events, there were major floods, and then all bets are off and the sites are gone. If we look at the Beas study that we did, we centered it in the vicinity of Harappa, and we went down to a number of sites that were along the way. And I think one of the big advantages that we had is a lot of these sites were very small. So some of the smaller sites allowed us to apply a different approach to how to understand these mounds, because the mound itself can be daunting. I mean, Mohenjo-Daro extending for 40 kilometers, Harappa being so extensive, these are complicated issues to approach. Smaller mounds, a little more convenient. Now, up in the upper Indus, the 5 rivers are separated by doabs, which are interfluves that essentially split out the direction and the flow of each channel unless there's a major flood zone, and it basically falls within the channel itself and proceeds in a downstream direction. One of the things that we thought would be the best thing to do would be to look at the intersection of the edge of the mound and the natural surface, because that tells you where the natural surface is sealed. And when you get that information, you can date it. So you can figure out exactly when people came to a certain landscape and started to live there. This is an example of one of our sites in, along the Beas, a large site. Afzal Khan is sitting over there. He was a little younger back then. And you will take a look and see exactly the sorts of things that you see at a representative mound. You will see a couple of breaks in the stratigraphy. You see the salt accumulating on the edge of areas like kilns and manufacturing zones. And that's how it goes. Now, when you get to the edge of the site, that is where the interesting information really is. Because you can see the course of the bricks, right? The break in the stratigraphy. What you see underneath it is a soil horizon. A soil is not a river deposit. It's a river deposit that has undergone weathering and has been stabilized. So there you would get a formal soil scientist to look at these horizons. And it's a very clean break. It's a stable surface. People live on stable surfaces. You can tell that the mud brick is right there. There is mound collapse above it, and then there's all the nonsense on top. And basically, most mounds, most even larger sites have some variation of this, albeit on a scale that can range anywhere from 2 to thousands of orders of magnitude above that, but this is the basic site formation process. And once you look at that, then you have sort of a guideline for trying to look at larger mounds. The little squigglies over there between these 2 mounds are soils. Those identify stable surfaces. So what we've done here is we have actually dated these, because the organic carbon in the organic upper material, the organic formerly grass surface of the mound, will give you an excellent date. And in this case, we had a succession of surfaces that went from 13,000 years ago to 6,000 years ago to about 3,000 BC, and areas and time frames like that. I meant 9,000 years ago, and then 6,000 to 5,000, which is of course, when the mound situation starts. So you have this excellent break between the mound itself and the natural landscape. And one of the benefits of that is you could sort of identify the preconditions that led to settlement of a particular place in time, so that those conditions were favorable. Again, looking at those soil horizons as an index of a favorable place to live. Now, way back in '97, we found out, with the help of Mark Canoyer, that essentially the subsurface of Harappa had never really been dated. So we climbed down into that deep trench, and we actually took a radiocarbon date of the very last deposit that preceded Harappa itself. And that was a Pleistocene date, a late Pleistocene date. It was well older than obviously than the earliest cultural material by about 6,000 years, but nevertheless, it gave us an indication of when this landscape was suitable for settlement. Then, and this is an older publication of ours, we looked at Harappa, Mound AB, a couple of the smaller and medium-sized mounds.